Afternoon, grade 11s. Today we're going to be continuing on in our solutions unit. We're going to be looking specifically today at dilutions. We are at 8.7 and 8.8 of your textbook. The pages can be found down at the bottom of the page, so 403 to 410, 412 to 413. Okay. So what we're going to talk about today is the difference between a dilute and a concentrated solution. We're going to learn some dilution calculations, including percent volume by volume, percent weight by volume, and percent weight by weight. And we'll finish up looking at the difference between parts per million, parts per billion, and parts per trillion. You guys took a look a little bit at this when we looked at our water contamination documentary last week. We're going to talk a little bit more about the math behind how that's calculated. We'll do some practice problems, and then we'll end off with some practice problems or activities from your textbook. So by the end of the class, you should be able to determine how to dilute a solution appropriately, express concentrations in all of these ways, and know how to perform a dilution in class. Obviously in distance learning, where we can't do that in class as we normally would, but you'll have the skills and know how should and when we return to the lab. Okay, so we have lots of dilute and concentrated things all around our house. So for example, you may have made orange juice from a can like this before, and we often call this orange juice concentrate. Well, orange juice concentrate has a really high amount of like the sugars and everything else that's in juice for a very small amount of solvent or water volume. Okay, so what you would do is you would take this really concentrated, so a lot of solute per volume of solvent. Orange juice concentrate, you wouldn't want to melt this and drink this straight. It would taste really sweet, really sour as well. It wouldn't taste like how orange juice should taste. You take that and you would water it down or dilute it to get the orange juice to the concentration you would like it to be. Okay, so we would add extra solvent to the same amount of solute that is in the can, and we would get a more dilute and more tasty solution. We often see this a lot of time with cleaners as well. You may buy an ultra concentrated laundry detergent or carpet cleaner. You may see on the label that it's 2 times concentrated or ultra concentrated. All that means is you're buying more solute, like the soaps and all the ingredients that do the cleaning, for a smaller amount of solvent, so the water. That benefits us in a few ways. It means that our packaging is usually smaller, so the price can go down because we're not paying for a bunch of plastic that's just holding water. It also means that the shipping usually is cheaper because they can ship greater quantities and the same amount of space. And it's also usually better for the environment because there's less trucks moving around this smaller bottle of product or airplanes moving it from one place to another. So often solutions that we come in contact with in our everyday life may be concentrated on purpose for different reasons. Now, move myself a bit up here. Out of the way. Okay. Many solutions, like we saw in that orange juice concentrate, need to get diluted. So watered down is sort of how we would typically use the language in everyday language. Okay. So to determine how much of a solvent, so again, remember, often that may be water, it's whatever's in larger quantity, we need to add to dilute a solution to a specific concentration we want. We use the following equation, which is our dilution equation, which says C1V1, or the initial concentration and the initial volume, is always going to equal C2 times V2, or the secondary concentration where we're going to end up with, and the secondary volume. Okay. So I'm going to make myself disappear here and we'll go through some of these calculations. This says, what's the final concentration when 250 milliliters of a 16 mole per liter nitric acid solution is diluted to 4.5 liters? Okay, so what this question is saying is we're starting off with a solution, okay, and this solution is 250 milliliters, okay, and the solution itself is 16 moles per liter. Okay. What we're going to do though is I'm going to add water to this to dilute it. Okay. And my new solution is going to be 4.5 liters. So I've added 4.25 liters, right? Because 250 mils, I've added 4.25 liters to make the new solution. in total, 4.5 liters. They're asking, what's this new concentration? Okay. So the only thing that's tricky, dilution calculations in and of themselves aren't tricky. What's tricky is making sure that you're keeping all of these as your ones and all of these as your twos. Okay, you want to separate these two numbers. You don't want to get a 1 mixed up with a 2. So this is going to be our V1, this is going to be our C1, this is going to be our V2. We don't actually know what our C2 is. That's what we're calculating. Okay. So how we're going to do this is we're going to say, okay, my initial concentration times volume is going to equal my new concentration times my new volume. Now, initially, my concentration was 16 moles per liter, and my volume, remember, we're going to keep this in liters as well because our molarity is still in moles per liter. So we're going to put this as 0.250 liters is going to equal my new concentration. I don't actually know what that is. That's what I got to calculate for. That's my mystery. Okay, but I do know my new volume is 4.5 liters. Okay, so to get C2 by itself, I'm going to divide both sides by 4.5 liters. So that's telling me that my C2 should be 16 moles per liter times 0.250 liters, all divided by 4.5 liters. These two are going to cancel each other out. If I put that in my calculator, I get C2 being 0.8889 moles per liter. But again, remembering sig figs, this number here has 3 sig figs because this 0 has a number to the left of it. This also has 3 sig figs because this 0 has a number to the left of it. This number right here only has 2. So I'm going to round this to 0.89 moles per liter. Again, we did learn yesterday you also could write this as 0.89 mol per L, or you could write this as 0.89 in square brackets. All of those things mean the same thing. And again, if we think about this, it makes sense. We started off with a really high concentrated solution with 16 moles per liter, and I added a bunch of water to it. So I diluted it and made it weaker. It makes sense that the new number I'm getting is much, much smaller. Okay. This practice problem says, what's the final concentration when 4.5 liters of a 3 mole per liter solution of car battery acid is diluted to 20 liters? Okay, so same thing. My initial concentration in volume is going to equal my secondary concentration in volume. I started off with a solution that was 3 moles per liter. That was my initial concentration, and 4.5 liters. I don't know what my new concentration is, but I do know it's diluted, so it should be less. It should be a number less than 3. My new volume is 20 liters. Okay, so to get C2 by itself, I'm going to divide both sides by 20. Okay, so if I take 3 times 4.5 and I divide that by 20, I'm going to get 0.675 moles per liter is my new concentration. Okay, but if I look at sig figs, this guy's got 2, this guy's got 2, this 0 has a number to the left of it, so it is significant, and this has 3, so I'm going to report to 2 sig figs, so this is going to be 0.68 moles per liter, or 68 moles per liter, or in square brackets. Doesn't make a difference. Okay, so again, you don't need to ask me, Miss, how many decimal places should we leave this to? Because from now on, now that we know how to report significant figures, we're going to always report to based on information given to us in our question. Okay. Now, molarity is arguably in chemistry the most common way we're going to report concentration, but it's not always the way we report concentration. We also can express things in a percent volume by volume, percent weight by volume, or percent weight by weight. We also often use parts per million, parts per billion, parts per trillion. These often are used more in like everyday products. So for example, if it's used in things like medicine or hair bleach, These are scenarios where the people who are using them may just be your typical consumer that don't have experience with a lot of chemistry, and so they may not understand what a mole is, right? Like we know not everyone takes grade 11 chemistry, and if you don't take grade 11 chemistry, you're not going to know what a mole per liter is, so it's hard to interpret that information. Parts per million, parts per billion, parts per trillion are often used if it's in a very, very small quantity, okay? So often things like water contaminants are going to be reported in parts per million, parts per billion, and parts per trillion just because it's so teeny tiny that we need a better unit of measurement. Just like you wouldn't measure the width of your hair in kilometers, doesn't make sense. These we would use in much smaller quantities, okay? So all these formulas are going to look almost exactly the same, okay? They're also very easy to use. It's just depending on whether you're looking at a volume or a mass, okay? So in percent volume by volume, essentially you're just looking at, in terms of a percentage instead of moles per liter, how much of the solution is made of the solute. You may see something like isopropyl alcohol or hydrogen peroxide. That's not going to be reported in moles per liter. It's going to be reported in a percent volume by volume. So in this case, it's 91% by volume, which means of this solution, 91% is the isopropyl alcohol, and the other 9% is water. Okay, so you would know the strength of the solution just based on that percentage. So here's an example. It says the concentration of ethanol in a 750 milliliter bottle of wine is 13.5% volume by volume. Assuming the wine has the same density as water, calculate the volume of ethanol in the bottle. Okay, so we're going to say that our percent volume by volume is going to be the volume of our solute over the volume of our solution, okay, multiplied by 100%. Okay, I'm just copying that formula from right here. You can label this as the solvent, or you can also think of this as the total volume of the solution. Both are fine. Okay, so what they're saying is the total solution is 750 milliliters. Okay, I'm going to convert that into liters just because I'm in the habit of doing that. Okay, and we don't know, it's asking us how much of the ethanol is in it, so we don't actually know the volume of our solute. That's what we're trying to figure out, but we do know that this is 13.5%. Okay, so to get volume of solute by itself, I'm going to divide both sides by 100 first. Okay, that's to get rid of this 100, so cancel this out. And I'm also going to multiply both sides by 0.75 liters. Okay, to get this by itself. So now volume of solute is by itself. So volume of our solute is going to be 0.750 liters multiplied by 13.5%, all divided by 100. So that's going to give us 0.10125 liters. Okay, but if I look at my question, this has 3 sig figs, and this also has 3 sig figs. So I'm going to report this to 0.101 liters. Okay, so what that's saying is in a, this work very well, in a 750 milliliter bottle of wine, 101 milliliters or 0.101 liters is ethanol, okay, if it's 13.5%. That's not always reported though. We can also report in something called a weight by volume, okay, and often what we're going to see this is written as vol, okay, on the side of a solution. And that just represents percent weight by volume. This is how much weight of solution, so that's going to be measured in grams, okay, is in a certain volume of solution. Okay. Now, this is often used in things like this is, for example, how you would measure hair bleach. Okay, so if you've been on YouTube recently, I'm sure you've seen that all these people are at home trying to color their hair, and some people have been making pretty bad mistakes coloring their hair or bleaching their hair. And a lot of times what they'll be talking about is what volume developer they used. Okay, so the higher this number, the stronger the bleach you're going to use. Okay, so you can buy like 10 volume, 20 volume, 30 volume developer for your bleach. Okay, the higher the volume, the more bleach, which is measured in a powder, is in a given amount of the solvent. Okay, so it's the same formula, it's just on the top here you're putting a mass instead of a volume. Okay, so this says, for example, glucose is used to prepare IV feeding solutions. What volume of a 5% weight by volume glucose solution would be prepared using 125 grams of glucose? Okay, now remember, if we put it in as grams, our volume is going to come out as milliliters because we know 1 milliliter of water weighs 1 gram. If we put it in as kilograms, our volume is going to come out as liters. So keep that in mind, okay? This one, because we're dealing with a small mass, I'm going to keep them in mass knowing that my solution is going to come out in milliliters, okay, instead of converting it to kilograms. So this, we're going to say the percent weight by volume is going to be the mass of the solute over the volume of the solvent, or the total solution, all multiplied by 100%. Okay. So they told us that the solution is a 5% solution, and we're told that we have 125 grams of glucose. Okay, so that's going to be the solute. We don't know how much solution that's going to make, so that's what we need to divide it by. Okay. So volume of solvent is on the bottom. It can't be on the bottom, it's got to be on the top. So I'm going to multiply both sides by volume of solvent times 5%. It's going to equal, this is 5%, 125 grams times 100%. And then to get volume of solvent by itself, I'm going to divide both sides by 5% to get rid of this, which is going to give me 2,500 milliliters. Okay. If we look at our question, 5.0 has 2 sig figs because the 0 has a number to the left of it. 125 grams has 3 sig figs. So I'm going to report this to 2 sig figs. So I could report this as 2.5 times 10 to the 1, 2, 3 milliliters. Or, because we know that there's 1,000 milliliters in a liter, you could also report this as 2.5 liters. Okay. So what that means is if I dissolve 125 grams of sugar, glucose, in 2.5 liters of solution, I'm going to make a 5% weight by volume IV feeding solution. Okay. The last one we're talking about for these percentages is weight by weight. A lot of medications or strong acids are going to report a weight on the side of the bottle, and this is a percent weight by weight. Okay. So often, for example, if you're taking like an Advil, you only need a very small amount of the active ingredient. We're talking about milligrams. So they don't make pills though that small because one, they'd be really easy to lose. Okay. And you wouldn't be able to see them very easily. So what they do is they add filler to the pills so that it's easier to see. Okay. So what you may report is they may tell you the percentage of the active ingredient. Okay, and that's going to tell you the mass of the actual active ingredient in the pill over the total mass of the pill. Okay, same formula though, but this time we're dealing with 2 weights instead of a weight and a volume or 2 volumes. So this says, for example, dissolving boric acid in water produces a mild antiseptic. That's something that disinfects. Okay, that's useful in eye washes. What mass of boric acid is present in 125 grams of a 2.5% weight by weight solution? In this case, we're going to say percent weight by weight. is going to be the mass of the solute over the mass of the solvent times 100. Now for this, if you put in grams for the 1 unit, what's going to come out is also in grams. If I convert this to kilograms, what's also going to come out is in kilograms, okay? The units are going to be the same. So we know this is a 2.5% solution. We don't know how much boric acid is in it, so this is our unknown. But we do know the entire solution is 125 grams. Okay. So to get rid of 100, we're going to divide both sides by 100. And to get rid of 125 grams, we're going to multiply both sides by 125 grams. Okay, so that's going to be the mass of our solute is going to be 125 grams multiplied by 2.5%, all divided by 100. That's going to give us 125 times 2.5 divided by 100 is going to give me 3.125 grams. But again, if I look at the question, I have 3 significant figures here, 2 significant figures here. So my final answer is going to be 3.13 grams. Okay. So all 3 of these calculations are really the same. It's just, are you putting in 2 masses, 2 volumes, or one mass, 1 volume? The last type of concentration we're going to talk about are extremely low concentrations. So sometimes the amount of a solute in a solvent is so teeny tiny, none of the measurement units we've talked about so far are appropriate. They're just too big. Like I said, it would be the equivalent of trying to say, my hair is this fraction of a kilometer wide. Okay, it's such a tiny amount, it doesn't make sense. So often in these types of calculations, we would use parts per concentrations. Okay, and these are special types of weight by weights, but really, really, really tiny amounts. Okay, so because these solutions are so dilute, we assume that the density of the solution is exactly the same as water because there's so little dissolved in it. So we would assume that any 1 milliliter of solution is going to contain a gram. Okay, and the formulas we can see is all really the same. Okay, it just depends on what unit we're talking to it to. So they're all going to be, they're not a percentage anymore. So instead of multiplying by 100, we're actually going to multiply by 10 to the power of 6. Okay. If it's a million, because million has 6 zeros, if it's a billion, we're going to times it by 10 to the 9. And if it's a trillion, we're going to multiply it by 10 to the 12. Okay. The units that it's going to come out in as well, remember, we're talking about really, really tiny amounts. So if I have 1 part per million, there's going to be 1 gram of that solution and any in 1 million grams of this entire solution. In parts per billion, there's only going to be 1 gram of solute per billion grams of solution. And in parts per trillion, there's only going to be 1 gram of the solute in a trillion grams of solution. So for example, if they say you have lead in your drinking water at 2 parts per billion, it means that there's 2 grams of lead and 2 billion grams of solution. Okay, these are all the same units, just in slightly different measurements. Okay, so here's a practice problem we're going to do. It says in a 1.5 liter sample of pool water, it contains 4.5 milligrams of chlorine. Determine the concentration of chlorine in parts per million. Now, keep in mind, we're really looking at how many milligrams are in a liter. Okay, 1 parts per million is milligrams per liter. So we're going to keep this in milligrams. So parts per million is going to be the mass of our solute times the mass of our solvent times 10 to the 6. Okay, but we need this liters to be in milligrams because we need this to be in milligrams. Okay, so this is going to say is 4.5 milligrams, but we need to convert 1 liters of water into milligrams. Okay, so we do know 1.5 liters is the same thing as saying 1,500 milliliters. Okay, which is the same thing as saying 1,500 milliliters is the same thing as 1,500 grams. But we don't actually need this in grams, we need this in milligrams. We need both of these units to be in milligrams. Okay, so there's 1,000, oops, pen's not working. There's 1,000 milligrams. Oh, my pen does not like that spot. Okay, so there is 1,000 milligrams in 1 gram. Okay, so that means 1,500 grams. If we multiply that by 1,000, we're going to get 1,500,000. Okay, milligrams. To make this a little bit easier, I may also say is equal to 1, 2, 3, 4, 5, 6. 1.5 times 10 to the 6 milligrams. Okay, so if I put that in here, I have 1.5 times 10 to the 6 milligrams times 10 to the 6. Well, these 10 to the 6's can cancel each other out. So I'm really left with 4.5 divided by 1.5, which gives me 3 parts per million. Okay? So you could also just remember, in general, 1 liter, I'm not liking that spot up here, 1 liter is really equal to 1 times 10 to the 6 milligrams. So if you just add, if it's in liters, if you add times 10 to the 6 on the end, you're going to get how many milligrams you have. Okay? So we have 3 parts per million there. Now, here's your homework for tonight. There's 4 questions. Remember, there are answer keys in your textbook, and the solutions that we just went through should help you. Reach out for extra help if you're having problems with any of these practice problems. And I hope you're staying home, staying safe, and staying healthy. Hopefully talk to you guys soon.